Okay. Thank you very much. And okay. So this lecture is still on this arithmetic degree. And in the end of last lecture, we talk about this theorem of Kawaguchi, Silverman, and Matsuzawa upper bound for the arithmetic degree. So it says that for every point x, if the orbit of x is well defined, then the upper arithmetic degree is at most the first dynamical degree. So it is one set of the Kawaguchi-Silverman conjecture, the upper bound set. And now we want to give this proof. Okay, and as we explained in last 10, the idea is that we give two height inequality, and we try to combine these two inequality to get this upper bound. Okay, so first, we may assume that we first do some reduction. We assume that the orbit of the point x is Zariski dense. Otherwise, we can replace this x by the Zariski closure of the orbit of x. So in fact, this may be not so correct because here we assume x to be irreducible, but the Zariski closure of this orbit might not be irreducible. But it's not a big problem because you can always replace this f by some iterate, and you can make some irreducible component to be invariant, and then you can apply everything to this irreducible component. So okay. So now we want to describe these two inequality. So first we give this we call it TB, so it's a trivial bound. But the advantage is that this trivial bound works everywhere. Okay, the trivial bound is the following lemma. So there is a constant C1 larger than 0, such that for every point x, which is not in the indeterminacy locus, then the height of the image of x is less equal to C1 times the height of x. Okay. And the proof is indeed quite simple. So first you take a resolution of this f, means that you take some bidirectional model x1 of x to make this f to be a morphism. To make this f to be a morphism pi 2, and indeed, we can assume that this pi 1 is an isomorphism above outside the indeterminacy locus of f, because if it's outside the indeterminacy locus, you don't need to do resolution. Okay, so we may assume that pi 1 is an isomorphism outside IF. So now we consider the following shift. So the following, in fact, is a line bundle. So you just pull back L by this pi 1 to x1 and tensor it m times, and then you tensor the inverse of pi 2 star L. Okay, and now you consider the push forward of this shift. So what you get is L tensor M tensor pi push forward, pull back L minus 1. Uh, so because L is ample, so if you take M sufficiently large, then pi 1 star F M is generated by global sections. It means that there is a surjective map of shifts phi from OXR uh, for some R maps to this map to this pi 1 push forward FM. And and then um, and then you have a because you have a nature. Okay. Because you have a nature morphism from pi 1 pullback, pi 1 push forward FM to this FM. So we compose these two morphism. Then we get a morphism from pi 1 star OXR to this FM. And pi 1 star OFR is just the arcans of the structural shift of X1. And we denote by phi 1 this composition. So because phi and phi 1 are isomorphism, offset in the indeterminacy locus. So so this phi and okay. So what I mean is that this pi 1 is an isomorphism outside the indeterminacy locus. So if you remove the indeterminacy locus, this phi and phi 1 are the same. So because this phi is globally generated, because this phi is globally generated, so it means that there is no base locus outside the preimage of IF. So it implies that the base locus of FM is contained in this pi 1 minus 1 IF. So now we can use the basic property for the height. We show that M M times H pi 1 star L minus H pi 2 star L is bounded from below on this on the preimage of X minus IF. Yes, and well, and because this pi because on this X minus IF, this pi 1 is an isomorphism. It's an isomorphism. So what you get is the following. So on X minus IF, we have this M HL large equal to HL compose F plus some O1. And then we finish the proof for this trivial bound. Okay, and okay, and now we give the second inequality. So the second inequality, I think it's more, it's a better bound because you see that in the trivial bound you have no control of the you have no control of this C1. So at least this C1 is not some optimal constant. But in here in this we call it a GB, so it's a good bound. This good in this good bound, we will have some better coefficient, and this coefficient will very close to basically it will very close to the dynamical degree, and which is what we want. Okay. The lemma is like this. So for every psi strictly larger than lambda 1, we can find some number n depending on psi large or equal to 1 and some constant C2 positive. And a proper closed subset B psi of X such that for every n large or equal to 1 and X in XF Q bar satisfying this iterates. So f n I x not contained in B for every I from 0 to n minus 1. We have the following inequality. So the height of f capital N small n x less equal to C2 times psi capital N small n h l x. Okay, so maybe we can just try to understand this statement. I think here the small n will tends to infinity. But basically, we want this small n to be very large. So if this small n is very large, then you can ignore this C2. So the right hand side is just this psi, and you see this psi is any constant strictly larger than lambda 1. So you think this psi is very close to lambda 1. So you can think that this bound is very close to the optimal one, because I think lambda 1 should be the optimum. Lambda 1 should be the optimal one. So it very close to this lambda 1. And so what we pay? What we pay is that we cannot get this inequality for free. We need this sequence of iterator of x. So this sequence f n I x for I from 0 to n minus 1. We need this sequence of points not contained in some bad locus B. So if we can avoid B, then we get this better estimate. Okay. So now we prove this good bound. I think this good bound is also based on this Schuss inequality. So for every n large or equal to 1, we consider the following resolution. I think this resolution is as before. We consider this resolution xn pi n to x, where xn is some projective and normal variety, and this pi n is birational. Further, we will assume that this pi n is an isomorphism above x, remove the indeterminacy locus of Fn. And then we resolve this F to a morphism from xn to x. Okay, and now we apply Schuss inequality. We get that Fn pullback L. Okay, the last rule is not F, is Fn. It's F nth power. Here the power is an upper index. And what we write from xn to x, the index is on the below. Here is some typo. Okay, so we look at this Fn pullback L. It is less equal to d times degree 1 Fn over LD times pi n pullback L. Now we fix some constant Q for example, we can take it to be d plus 1 over LD. So this is strictly larger than d over LD. So we take this q to be slightly larger than the coefficient in the right hand side. So because it is slightly larger, so we can have some Bn effective such that this q degree 1 Fn pi n star L equal to Fn star L plus some effective devices Bn. Okay. So now, because this percent is larger than the dynamical degree, so you can find some n such that for n large enough, this q times degree 1 Fn is strictly less than percent n. So so now you can find a constant d large equal to 0 such that for every x whose orbit is well defined and it is not contained in Bn, we have the following inequality. So it's psi n HLX plus D large equal to HL Fnx. Then we get the following inequality. So it's psi n HLX plus D over psi n minus 1 large equal to HL Fnx plus D over psi n minus 1. So this is just a simple computation. Now, but we make the inequality in these forms, then it's easier to do iterate. Okay, so now for every n large equal to 1 and every x in xfk such that the sequence fnix not in Bn for every I from 1 to n. We get the following inequality. So HL F capital N small n x less equal to HL F n n x plus d over psi n minus 1 less equal to psi n n HLX plus d over psi n minus 1 and less equal to this C2 times psi n n HLX. And this C2 you can take it to be d over psi n minus 1 plus 1. Okay, so this finish the proof of the good bound. Okay, so now we do the second step. The second step is to now we have two upper bound, a trivial bound and a good bound, and we want to combine it. We want to combine these two bounds, and I think the key idea is the following theorem. We call it the weak DML. So you can think of it as some weak form of the dynamical model conjecture. I think this result was first proved by Favre, and but not completely in this form. And later it was has many people have many different proofs. So I read their proofs of Bell, Giacca, and Tucker, and Gignac, and I also give a proof for these things. And the statement is as follows. So for every point x in xf, with if it's with Zariski dense orbit, then for every closed subset, proper closed subset V, the density the natural density of n such that of the natural density of n such that fnx contained in V uh, is zero. In other words, is this set. So you consider fix. So for which I this fix is contained in V, and the uh, the proportion it tends to zero for n larger and for n tends to infinity. Okay. And so, for example, if you assume the dynamical Modellan conjecture, if you assume Modellan conjecture, uh, and in the case that the orbit of X is Zariski dense, then indeed you can show that the orbit of X only meet V finitely many times. So of course, if so, it's a finite set. So of course, the density is zero. But the in general, the dynamical Modellan conjecture is very hard. So it's still very open. So here we just use this weak form. So the weak form is that okay, we cannot prove it is a finite set, but we can still prove that the density is zero. Okay, so now we pick for every psi strictly larger than lambda 1 by this good bound. There is n and C2 n large equal to 1 and C2 large equal to 1 and a proper closed subset B in X such that for every n large equal to 1 and X in XF bar, if this sequence Fn Ix not in B for I from 0 to n minus 1, we have this GB. So HL Fnnx less equal to C2 psi Nn HLx. Okay. And for every point y in XF Q bar, we just we just set this Wn to be the set of 10 such that Fniy contained in B. So I think it's the bad 10 because you think the B is a proper subvariety of X. So it's it's some set of no dimension. So usually you said if you take a point randomly in this X, it cannot contained in this. It has probability zero contained in this in B. So you think that this Wn is some bad 10, so it's the 10 such that it's very unlucky. This orbit is drawn in B, and you denote by this small Wn to be the number of Wn. So the dynamical Modellan conjecture implies that this small w, the weak dynamical Modellan, the weak DML implies that the quotient Wn over n tends to zero. Okay, so now we remove this bad set. So we consider from 0 to n, but we remove the set in Wn. And if we remove this bad set, then we can write it as some disjoint union of some kind of connected component. So the maximum consecutive numbers. So I think it's very simple to see in this following example. For example, we take this n to be 10, and this Wn is contains three numbers. One is 3, and another it's 3, 6, and 7. So if you remove this Wn, then we divide the rest set to be three connected components. So it's 0, 1, 2, 4, 5, and 8, 9, 10. Okay, so what we want to do is that we apply this good bound for each connected component. So for each connected component, we apply the good bound, and for others, for the 10 in this for the bad 10 for the 10 in this Wn, we apply the trivial bound. Then we get the following inequality. This inequality is something like we mix this good estimate and the bad estimate together. So we get this HL FNNY less equal to C2 Wn plus 1 C1 2Wn psi capital N N minus Wn HLY. And then we take limit. We get this alpha f. So maybe this y is x. So alpha f x n. The upper bound is equal to you can this is property of the arithmetic degree. So if you iterate this f, you just change the arithmetic degree to be some power. So you get alpha f fn the upper bound upper y. And it equal to the limit sup of HL f nny 1 over n. And then you apply the above inequality. You get limit n tends to infinity C2 Wn plus 1 over n, C1 2 Wn over n, psi n 1 minus omega n over n. But here you use you know that this Wn over n tends to 0. So the limit is just psi n. So it implies that this upper arithmetic degree is less equal to psi. And this psi, you can, because this psi is arbitrary number strictly larger than lambda 1. So you can take this psi converge to lambda 1. Then you get this alpha f bar y less equal to lambda 1. So you finish the proof. Okay, so now there is one ingredient, the weak DML we didn't prove. So I will give the proof of this weak DML, and here I follow my proof. And the idea of my proof is to use this ergodic theory, but for the constructible topology. So I think many people know what is constructible topology, but I want to still recall it. So the constructible topology is the topology on X generated by the constructible subsets. And you can also think it as the topology generated by all Zariski open subsets and all Zariski closed subsets. So it is finer than the Zariski topology. And if you put X with this constructible topology, you can show that this space is Hausdorff and compact. Okay, and we just denote by this the norm of this X to be to be the set X with the constructible topology. And now we denote by this M1 X to be the space of probability random measure on X with the weak star topology. So maybe I just explain what is a random measure. A random measure in this case, it means that for every Borel subset B of X, the measure of B is the sup of the measure of compact subset contained in B. But indeed, we don't really need we in the end we don't really need to end this condition of random measure, because in the end you can show that this space X with the constructible space is indeed a random space. So any Borel measure on any finite Borel measure on X is indeed a random measure. Okay, but this is not so important for our proof. So we can end this random condition, and this space is indeed you can find that this space is quite simple. So we have this the following lemma. So every probability measure in this M1X, it is indeed a combination of some Dirac measure. So it's a countable combination of Dirac measure. So it's mu equal to sigma AI delta xi, where AI large equal to 0 and the sum of AI equal to 1. And the proof is just by the nonlinearity. And because X is compact and Hausdorff, so it's a general fact that the space of random measure is also compact. So this is a general factor in functional analysis, and but in fact, in this case, we can also show that this space is not just compact; it's also sequentially compact, and the proof is also by nonlinearity. So we just omit it here. Okay, and now for the simplicity, we assume that our self-map F is an endomorphism. So because in our setting F is a rational map, but for the simplicity, we just assume it is an endomorphism. So it's well defined everywhere. Okay, so recall that in our case, we assume that the orbit of X is Zariski dense. Now we define for every n we define a measure. This mu n is the average. In fact, is a Birkhoff average of this x. So it's the average of the Dirac measure on every fi from 1 to n from 0 to n minus 1. So it's a probability measure. So we claim that this mu n converge to the Dirac measure at the generic point of x. So we first prove this claim. So because this M1X is sequentially compact, so we only need to show that every convergence subsequence mu ni converge. For every convergence subsequence mu ni converge to mu, we have this mu equal to the Dirac measure at the generic point, so delta mu. So we observe that if we push forward this mu ni, it just equal to 1 over ni, and then you do the average from fx to fnix. So so basically you find that basically it does not change. It only changes the first term and the last term. So you just write it as mu ni plus 1 over ni delta fni x minus delta x. But you see that the second term in fact tends to zero. So when you taking limit, what you get is that the push forward of mu equal to mu. So mu is an F invariant measure. So now by our lemma one, you can write this mu as some as at most countable combination, a positive combination of Dirac measure. So you write it as this sigma ai delta xi, where ai are positive number. Now you use this because this mu is F invariant, and it implies that each xi is periodic. Each xi is periodic. So now, if our claim does not hold, means that this mu has you have some term xi not equal to the generic point. So we may assume this I equal to 1, and we can after some iterate of f, we may assume that this f xi are equal to xi. Now we denote by z the Zariski closure of this x1. So because x1 is not the generic point, so fz is contained in z. And we have fz contained in z, and z is not the whole space. And here we have observation. So because z is Zariski closed, so it is both open and closed in the constructible topology. So the correct function 1z, the correct function of z, it is indeed a continuous function for the constructible topology. So you look at the integration 1z on this mu ni. This integration, because mu ni is just a Birkhoff sum of the orbit, so this integration is just to count how many from 0 to ni, how many fjx contained in z. And because this mu ni tends to mu weakly, and this correct function is continuous, so it converges to this integration of 1z mu. And because this mu has some mass, at the generic point of z, so this integration is strictly larger than 1, is strictly larger than 0. So in other words, it implies that for some iterator r, this frx, for some r, frx is contained in z. But this z is F invariant. So for every n large equal to r, the fnx always contained in z. But z is not the whole space. So this implies that the orbit of x is not the whole space. So we get a contradiction, and this implies our claim. Okay, now we can finish the proof. Now we take any proper closed subset V of X. Because V is a proper closed subset, so it do not contain the generic point of X. So now you count the 10 such that Fix contained in V. It is just the integration of 1V by the measure mu n. But but this mu, because this mu n converge to the Dirac measure of the uh, generic point, so it converge to this integration 1v delta eta, and because eta is not contained in v, so the right hand side is zero. So we finish the proof. Okay. So I think now it's I think this indeed we have this three conjecture. One is the dynamical model long conjecture. Another is the Zariski dense orbit conjecture, and we have also this Kawaguchi-Silverman conjecture. All these three conjecture are about orbits, So they should be very close to connected together. So I think one idea to study, for example, one idea to study this Kawaguchi-Silverman conjecture in this recent research. The idea is not just do this conjecture itself. We combine all these things. We do this Kawaguchi-Silverman conjecture, the Zariski dense orbit conjecture, and the dynamical model conjecture together. And I think there are several works in using these ideas. I think there are works by myself and by Jia Shibata, myself, and De Qizhang, and Masuzawa, and Wang Long, and myself, and with Masuzawa. And I want to give an example to explain how we can how it works. So I think one typical case is this thing works quite well. Is this one hyperbolic case? So we say this is one hyperbolic means that this map is cohomologically hyperbolic at the first index. In other words, it means that this lambda 1 f strictly larger than lambda 2 f. And if you draw the graph, it just means that the dynamical degree is strictly decreasing. Okay, so our assumption is that this F is a dominant rational self-map on X divided over Q bar, and assume the dimension of X is D. As before, we denote by this XF to be the set of Q bar points whose orbit is well defined. And in fact, there is also a question. So it's not trivial that this space is non-empty, and it was proved by America that this space is indeed non-empty. And in fact, if you look at the proof of America, and if you use this, I will give more detail later. If you use this adelic topology I introduced, indeed, you can show that for in this adelic sense, almost all points are almost all q bar points of X are contained in this XF. So this set is not only non-empty, it's indeed quite large. It's many. Okay, and we first give the first result is this theorem one is first given by Masuzawa Wang in some special case and then Masuzawa in the general case about this Kawaguchi-Silverman conjecture. Uh, what they prove is the following. So for every x in this xf, if you further assume that the fnx, the orbital of x, is generic, then they show that the arithmetic degree alpha x is well defined, and moreover, it is contained in the finite set mu from mu1 to mu_d. And how it applied to the Kawaguchi-Silverman conjecture is the following. So if you assume if you assume further that RF is one hyperbolic, then you look at this set mu1 to mu_d. There is only one element larger than 1. All others are strictly less than 1. So only mu1 larger than 1. All these mu2 to mu_d are strictly less than 1. But we know the arithmetic degree is always large or equal to 1. So if you combine these two things, you get this arithmetic degree. It can only equal to mu1. And because mu1 is indeed equal to lambda 1. So this this give you this proves the Kawaguchi-Silverman conjecture. Okay, so now we give the proof. I think the key idea of the proof is also the recursive inequality. So now we pick any L in this peak tilde x big and nef. Because this mu I is decreasing. So we have a minimal I. So it's minimal, not maximal. There is a minimal I such that f alpha bar x strictly larger than mu I. Okay, but we know that the alpha f bar is less equal to mu1. So this implies that I at least 2 and mu I minus 1 strictly larger than mu I because this I is minimal. And also we have this mu I larger equal to here I also have a typo. It's mu I minus 1 larger equal to alpha f alpha x f x bar. Okay, so now we apply this recursive inequality. The recursive inequality shows that for every epsilon in Z0 and Z1, we think this epsilon is close to 1, and M sufficiently large. This line bundle MM equal to L2M plus mu I minus 1M mu I M L minus mu I minus 1M epsilon M L M is big. Okay, so in the end, we still want to use the easy lemma to get the conclusion. So we need that the three conditions. So we explain here what are these conditions. So the first, you look at this alpha f bar x larger than mu I. This inequality will give you, in the end, will give you the the initial condition. Yes, this will give you the initial condition. But I don't know why I write ni. Maybe in or ic, something like that. And uh, and here, if you take this m sufficiently large, because mu I minus one. Okay, because this, I also have a typo here. So because mu I minus 1 is strictly larger than mu I, and if you take this epsilon very close to 1, the left hand side is mu I minus 1 m epsilon m. It will strictly larger than mu I minus 1 m plus mu I m. So if you take this m sufficiently large, so this will give you the non-degeneracy condition. Okay, now you fix HL V hat for L, and then you get a V hat H M. It is a V hat for M, and you can write it as HL composed F 2M plus mu I minus 1M mu I M HL minus mu I minus 1M epsilon M HL composed FM. And we denote by this Bm some stable base locus of mm. So for the simplicity, we assume this m equal to 1, and we drop all this index m. So now, because the orbit of x is generic, it implies that for n sufficiently large, if Fn x will not contained in B. And so it is not contained in the stable base locus. So this implies that, and then you also need to apply the you can also apply this Northcote property. What you get is that for n sufficiently large, this hat HM composed Fnx is positive. So you get this inequality. So this HL composed Fn plus 2x plus mu I minus 1 mu I HL composed Fnx large equal to mu I minus 1 epsilon HL composed Fn plus 1 x. So this is a recursive inequality of numbers. The numbers are this height are this HL composed Fnx. So this is a sequence of a positive number, and you get this recursive inequality for these numbers. Then you can apply the simple lemma, which shows that the limit info of this HL Fn x 1 over n large equal to mu I minus 1 epsilon. But this limit info is indeed the lower arithmetic degree of x. So now you can take this epsilon tend to not tend to 0, epsilon tend to 1. If you take this epsilon tend to 1, then you get this r, the lower bound, the lower arithmetic degree of x is large equal to mu I minus 1. But you already have that the upper arithmetic degree is less equal to mu I plus 1. So if you combine these two inequality, you get that the arithmetic degree of x is well defined and equal to mu I minus 1. Okay, so if you look at the proof of this theorem one more carefully, you can get a more precise result, which is the following. We call it the corollary 2. This is proved by Matsuzawa and Wang. Um, so assume lambda 1 strictly larger than lambda 2. Then for every epsilon strictly larger than zero, you have a directly open subset, non-empty directly open subset U epsilon, such that if for n sufficiently large, Fnx is contained in this U epsilon, then the lower arithmetic degree is largely equal to lambda 1 minus epsilon. So here is something like uh, you don't really assume X to be generic. You just need for every epsilon you have some directly close some bad locus, and if this X can avoid this bad locus for n sufficiently large, then you can still get some control from below of the arithmetic degree. And I think how can you use these things is indeed you want to have many points which satisfy this assumption. So the assumption is for n sufficiently large, Fnx is not contained in U epsilon. And if you use the language of adelic topology, you can show that in the sense of adelic topology, almost all points satisfy this condition. So in particular, if almost all points satisfy this condition, it implies that there exists one point satisfy this condition. So in fact, it implies that for every epsilon larger than zero, there is a point x whose arithmetic degree is largely equal to lambda 1 minus epsilon. Okay, so I think this is something, how can we say, is something that very close to Kawaguchi-Silverman conjecture. So it's we don't directly prove the Kawaguchi-Silverman conjecture, but we want to construct some point whose arithmetic degree achieve the maximum one. And what they prove is that we can have many points whose arithmetic degree is almost the maximum one. But you will see later, indeed, if you can get such a point, many points very close to the maximum one, then you can get one point, which you can also get many points by some argument, which not up to epsilon, it exactly equal to lambda 1. But for this, we need to first briefly introduce the adelic topology. So this topology was introduced by myself. It is a nature. In our case, it is a very natural topology on the set of algebraic points on X cube R. And it has the following. I don't want to give the precise definition, but I only want to give some property of it. So the first property is that this topology is finer than the Zariski topology. But it is still non-Hausdorff. In fact, it is in this case X is irreducible. So we can show if X is irreducible, then if you have two Zariski open subset, non-empty Zariski open subset, then their intersection is still non-empty. And this still works for this adelic topology. So if you have two adelic open subset, then their intersection is still non-empty. And the any flat morphism between varieties are open for this adelic topology. And there are also some other properties. For example, the action of the Galois action is continuous for this adelic topology, and so on. Okay, and but indeed, what I usually use this topology is not use it as a topology. How I use it is that we think it as a way to think almost all. So 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 we will use the following terminology. So we say some property holds for an adelic general point. Uh, so means that it works for every point on some non-empty adelic open subset. So I think the idea is that in many problems, sometimes you want to construct some point satisfy some property, but usually it is very hard to find one element. Uh, but sometimes it's easier to find directly many points. So basically, we don't prove there exists one point. We prove almost all points satisfy some property, and sometimes this makes things easier. Okay, so if you use this language of adelic topology, you find that you can make the statement of this corollary 2 a little bit stronger. So I just call it corollary 2 plus epsilon. And this is almost due by Masuzawa and Wang. So I think the contribution of Masuzawa and Wang is this is 1 minus epsilon. And what I did is epsilon. Okay. So the statement is here. So if you have lambda 1 strictly larger than lambda 2, and the sequence fnx is generic. Oh, no. What I say is if it is one hyperbolic, so lambda 1 strictly larger than lambda 2, then for adelic general point x, the orbit of x is generic. So this indeed have two consequences. First, because this orbit is generic, so its closure is Zariski. So this orbit is Zariski dense. So it indeed implies the Zariski dense orbit conjecture in this one hyperbolic case. Another consequence is you apply the theorem 1 of Masuzawa and Masuzawa Wang. You get that because in this case the orbit of x is generic, so the arithmetical degree equal to lambda 1. So you show that for adelic general point, the arithmetic degree is just the first dynamical degree. Okay. So now we give the proof. I think the key ingredient of the proof is the following proposition proved by me. It's as follows. So it says that if you replace this f by some positive iterator fm, then for adelic general point x, its orbit is the Zariski closure of its orbit is irreducible. and the orbit Fnx is generic in its Zariski closure. And indeed, the second statement basically say that the dynamical model. So we know the dynamical model along conjecture is quite hard in general, but the second condition just say that the dynamical model along conjecture holds for arithmetically general points. So if you want to prove the dynamical model along conjecture for all points, this is hard. But you can show some weak version is almost all points satisfy this conjecture. Okay, so now we pick any epsilon larger than zero, but strictly larger than zero, but strictly less than mu1. I think maybe it's not mu1, it's maybe it's mu2. Maybe it's mu2, but you can just think this epsilon is some very small. Epsilon is a very small positive number. Okay, so X is adelic general implies that because X is adelic general, it is general for Zariski topology. So X is not contained in U epsilon. And because X is contained in its Zariski closure, in the Zariski closure of its orbit, so we denote by Zx the Zariski closure of the orbit of X. So and because the proposition 3, this Zx is irreducible. So if Zx is irreducible and it contains one point not in mu epsilon, this Zx is not I think there is also a typo. So here what I write is the intersection of Zx and U epsilon is non-empty. Or in other words, what I read is this Zx is not contained in the complement of this U epsilon. Then you apply this the second part of this proposition because this orbit of X is generic in this Zx. So it implies that this Fnx is so it's contained. Not is here is also a typo. So this Fnx is contained in this mu epsilon for n sufficiently large. So now you apply this corollary 2. You show that the lower arithmetic degree of X is strictly larger than this lambda 1 minus epsilon. And because this lambda 1 is strictly larger than lambda 2, and this epsilon is very close to 1, is very close to 0. So this lambda 1 minus epsilon is still strictly larger than lambda 2. Now we apply the Kawaguchi-Silverman upper bound. We look at the first dynamical degree of the restriction of F on this Zariski closure, on this Zx. This one is large or equal to this arithmetic degree, large or equal to this alpha Fx. So it is strictly larger than lambda 2. But if you look at the definition of the dynamical degree, and it's not hard to show that you just use the definition. It's not hard to show that this first dynamical degree of the restriction of this Zx is less equal to the minimum of lambda 1 and lambda 1 plus the codimension of Zx. But in all case, it is one hyperbolic, so the dynamical degree is decreasing. So if the Zariski closure of X is not the whole space, then the second term is strictly less than lambda. The second term is less equal to lambda 2. So if you take a minimum, the right hand side is strictly less than lambda 2, then you get a contradiction. So it implies that the codimension of Zx equal to 0. So means that this Zx is the whole space. And because Zx is the whole space, and the orbit of x is generic on Zx, so it is generic on x. So it implies that this Fnx is generic. So this finish the proof. Okay, so in the end, I just want to give some question. So it's about what's the next for this. In fact, it's not really next because many problems we are already many works on this problem already. But I think it's still interesting in the future. So the first question is about the entropy in the non-Archimedean space. I think this is this is just at the very beginning of the study, the entropy in the non-Archimedean case. So even when F is a projective space and F is endomorphism, everywhere well defined, many basic properties are still open. So, for example, there is a conjecture of Favre, Tom, and me. So I think this should be a very basic property. So means that uh, whether the topological entropy is stable on the base change. So if capital K over K is an extension of a complete non-Archimedean field, then the entropy of Fk should we guess it should equal to the topological entropy of F. So basically, what we want is the topological entropy. It should be invariant on the field extension. Um, Under the field extension. We only know this only know the answer in some very special case. First, we know that there is one direction is easy. So the entropy of F capital K is largely equal to the entropy of F. This part is easy, and we can also show that if this capital K is contained in the completion of algebraic closure of K, then in this case we have the equality. But in general, we don't know. This is the first question, and I think the second question is about the equidistribution for equidistribution problems for the cohomologically hyperbolic maps. And here, what I mean equidistribution, I think we can discuss the equidistribution for many objects. We can talk about the pullback of orbits or periodic points. So here I only present it for periodic points. So here we let F to be a cohomologically hyperbolic self-map, rational self-map. And we already know that the periodic points of F is Zariski dense. And we also know that most of them, in some sense, are isolated. Uh, so we define this pair n prime f to be all isolated n periodic points. Okay, and I think we have the first. I think for this equidistribution problem, we have several level to do. I think the first level is to count the periodic points. So it's a counting problem. So if you assume that the f is I periodic, means that means that the graph of the dynamical degree is as follows. It takes maximum value at so there is a unique I such that lambda I takes the maximum value. So we guess that the number of isolated periodic points is almost lambda I n. Okay, so this is about the counting. So if the counting is correct, we can ask the algebraic, the equidistribution in the algebraic sense. So here we just denote by this mu n to be the average of the isolated n periodic points. Uh, and we think it as a measure for the constructible topology. So can we show that this mu n converge to the Dirac measure of the generic point? Uh, I don't know. So I want to ask this question. This is the level of algebraic, and then you can also ask it in the analytic level. So you assume that XF are defined over the field C or some non-Archimedean field, for example, CP, and we can still define this mu n as below, but here we view it as a measure on for Euclidean topology, and we want to ask, is this mu n converge to some kind of canonical measure, so some mu f? And in the end, we also have this uh, arithmetic. We can also have this arithmetic problem. So you assume this xf are defined over some number field, and this if you have some xn isolated periodic points, and you assume this xn to be generic, then if you fix any field embedding from K to C or some p-adic field, can we have this equidistribution result? So it's the average of the Galois orbit of xn converge to some canonical measure mu f as in the analytic case. And I think for polarized endomorphisms, all these four problems has a positive answer, and it's quite clear nowadays. But but in general, I think if the topological degree is strictly larger than others, then okay. So in the case that I think in the case that if the topological degree, the last dynamical degree is strictly larger than others, in this case, I think one, two, three are essential. I think the first three questions should also know, and I think in the arithmetic equidistribution is also known for some cases. So, for example, if X is smooth and rationally connected. And but in general, this question is quite open. So especially for rational self-map, I think for rational self-map, not many things are known. Even for surface. Okay, so I think the third class of question is to study the degree growth. So I think the arithmetic degree is the exponential part of the degree growth. But we also want to understand the sub-exponential part of this degree growth. For example, is it polynomial or something? And I think this question is well understood in some cases. For example, if x is dimension 2 and f is birational, it is already understood by Diller Favre, and I think maybe also maybe they also use the works of Giatulin and maybe Cantar or many people, and also by Favre and Johnson for endomorphisms of A2. And there is also a case that if the first dynamical degree lambda 1 square is strictly larger than lambda 2, uh, in this case, we can show that the limit of degree 1 fn over lambda 1 n tends to 1. Not tends to 1, but has a limit. Has a limit, and you also have some estimate of the uh, residual term. I think in the surface case, this is done by Bookson Falk, and in any dimension, this is by okay. Maybe I write some. This is not Falk Johnson. This is Falk Dang. So I get too many typos in this talk. I'm sorry for that. Okay. And I think I can finish my lecture here. Thank you very much.
So thank you, Junyi. You have some questions for Junyi? Many of them, yes.
Hello, Junyi. I have a question. If your map is ith hyperbolic, do you expect that the dynamical degree lambda I is algebraic?
I think not. You say it's I think we have an example that lambda for one hyperbolic maps. Not I have. I think it's Masuzawa and Wang. They have an example that for some one hyperbolic maps, this lambda one is not algebraic.
No more questions. Yeah.
Let me see. I forgot, but I think they have such example, but it's not a new example. It's some modify of it's something like you use the because basically we only know two examples for this transcendental arithmetic degree, but you can construct some example using this using these examples. So.
There's another question.
About equidistribution for cohomologically hyperbolic maps. You use Fakhruddin Punen's lift of a mod P periodic point to generic point, and are there bounds of the number of lifts or something? This is one question, and another question is why does the method doesn't work for, say, function field case? So spec Z, there are some lifts, but spec over the curve periodic point doesn't lift to the generic point, and why is this? So?
I think it lifts. So because for the talk I just want to keep in the simplest case, so I assume the base is just spec Z. But in fact you can do it. In fact the statement is very general. It's on any algebraically closed field. So you can do this lifts inductively. So. And for the equidistribution result, I think the problem is that if you just want to, so I think the idea is like this. So if you just want to show the periodic points is Zariski dense, then you don't really need to use all periodic points. You just find some subset of the periodic points and show this subset is characteristic dense, then it's okay. But if you want to prove the equidistribution, then you need to use all periodic points, and I think that's the problem. That's the problem. So because if you want to do the lifting argument, if you want to do the lifting argument, you use some Hushovsky's argument to construct some periodic points over some finite field. But in fact, Hushovsky's argument only give you a part of these periodic points, not all periodic points. So, and I guess the proportional of points constructed from Hushovsky's method is, I think the proportional should not be 1. So you cannot just use this point to prove the equidistribution.
A question for back, from back.
Hello. So,
Hello.
hi. Do you think this bound can be improved for you? Instead of asking lambda 1 bigger than lambda 2, you ask mu 2 strictly smaller than mu 1?
I think it's I think if you want to prove the Kawaguchi-Silverman conjecture in not one hyperbolic, but for example 2 hyperbolic, but with some condition, so lambda 1 mu 1 strictly larger than mu 2. I think it's you need some new idea, because how can we say? Because you see that all our argument not use number field so much. What we use this number field is just the Northcote property. But in the function field case, you can really construct some example such that the arithmetic degree can take all this mu I. So even you assume the orbit is this orbit is characteristic dense. So in fact, in one work, in one of my work, but unpublished work, I can prove that in the endomorphism case. So for an endomorphism of X, the arithmetic degree is always, if the orbit of X is characteristic dense, then the arithmetic degree is always one of the Lyapunov exponent. And if you in the function field case, you can also get examples to have some endomorphism such that for each Lyapunov exponent, you can find a point whose orbit is characteristic dense and the value is this mu I. So if you want to do the Kawaguchi-Silverman conjecture in general, you really need to do more arithmetic, I think.
Okay, so if there's no further question, let's offer our warmest thanks to Junyi for the series of lectures.
Thank you very much.